Hello everyone. So today we're going to take a little bit of a closer look at phasors, which we briefly touched on last time. So at the end of the session, you should be able to sketch the steady state sinusoidal VI relationships for RL and C components, derive the phasor form of impedances, convert between the time domain and phasor domain representations, and represent voltages and currents on a phasor diagram. So just to recap, we had this this was a slide from the last video. So phasors are a convenient way to represent AC parameters, and they are essentially anti-clockwise rotating vectors. Well, they look like them, but they're not really vectors. And what we do is we just take the magnitude of the sine wave and we represent that as in its RMS form. We convert it to RMS, and that will be the magnitude of the phasor. And then we take the phase shift of the sine wave and we represent that as the angle in the phasor. So I want to go back to this set of equations and look at how we derive impedances in phasor form, because these are the things that define the components. We have looked at representing voltages and currents like this. So we have the current here and then we have the voltage form here. And we saw that there are essentially three, for each component we get, which is three components, so we have three phasor forms for the voltages, 1, 2, 3. So I know that I is Im cosine omega t, and I can represent V is equal to Z, the impedance, multiplied by I. If I look at these phasor forms, I will see for VR that I multiply I by this value here, R. So I could say that ZR, the impedance of R, is R. Similarly, for VL, I have the I term here, and then I have this j omega L added in front. So I could say that ZL is j omega L. And for C, I get ZC is minus j on omega C. So these are what I would call the phasor impedances. So when I was dealing with DC, if you remember DC, the value of the frequency is 0, then you'll see here that if omega is 0, then the phasor impedance of the inductor goes to 0, which is a short circuit. And if the frequency goes to 0, then the impedance of the capacitor goes to infinity, which is an open circuit. So if it's not 0, if the frequency is not 0, then I get some non-zero value for those impedances. And this J here, if you remember the complex plane, J is on this side. So the resistor would be here, R. The inductor would be here, ZL. And then the capacitor would be somewhere down here, ZC. And this is, ZL is J, ZC is minus J. So if I represent this as an angle, this is 90 degrees for ZL and minus 90 for ZC. And we refer to these impedances of capacitors and inductors as reactances, and we often represent them with XC for the capacitor and XL for the inductor. So the important thing to remember about these impedances are that they are not phasors. Although we call them the phasor impedance, they are not phasors. They're just complex numbers. They don't have any frequency associated with them. I mean, although the value of the impedance is, say, j omega L, there is no rotation of this vector. This is a single quantity. So there is no t value. So if I looked at, say, it was equal to Im cosine omega t. So this omega was related to some time. So it meant that the value of this I changed in time, and I could plot it as a sinusoidal wave. That is not what happens with the impedance. With the impedance, it is just a complex number. It does not rotate or anything. It is a static complex number. So if I'm adding these impedances, I add them the same way I add complex numbers. So if I have a resistor and either a capacitor or an inductor, I could add that the same way I add complex numbers, which is that I could add the real parts together and the imaginary parts together, or I could represent them, and then I could represent them in polar form by taking the magnitude and the angle. So if I added an R plus JXL, I could represent that as simply R plus JX, or as a Z angle theta Z. And that again is simply the rectangular form, the rectangular or polar form of the impedance. So let's look at how we represent phasors as opposed to sine waves. So here I have two sinusoids. This one, if I had to represent it, would be cosine omega t, Vp cosine omega t, and that converts in phasor form to a vector of value of magnitude Vp on square root 2 with angle of 0. If I offset that by some value theta, then that becomes theta, the same value here, which is Vp on square root 2, which is the same as Vrms, with an angle of theta. Now notice the direction that theta is going here to make it positive here. So this is, as you can see, very simple to do. All I need to know is the magnitude and the phase. This is one is Vp cosine omega t plus theta. Right? So if you want to see why this results in a positive angle, then what you have to look at is at time 0 on this graph, the angle I have here, the value here, is the same as theta on this graph. So this is theta ahead, because at time 0 here I have already reached the equivalent of theta here when I have no plus theta. So that's why when you shift backwards this way, you end up with a positive. I hope that is not too confusing. So all I do simply to translate between the time domain and the phasor domain, as we just showed, was you take the magnitude, you turn it into the RMS, and then you look at what is the phase and you turn that into the angle. So plus theta will be theta here. If I have sine omega t, that is the same as cosine omega t minus 90 degrees, or minus pi on 2. So that is what will go here. So remember, the 0 degrees is for the cosine wave, not for the sine wave. You could choose to use sine waves instead, and everything will be relative to that, but whichever one you choose, you have to stick to that, and the convention is to use cosine as the 0 value. So what are the benefits in using phasors? Now that we've gone through the graphical part of it, you could see that if we have two sine waves, and this could be like the voltage across a resistor and the voltage across an inductor, it is the difference between summing these sine waves together or summing these vectors together, and I think we know which one is easier there. So the phasors really allow us to treat these sine waves as though they were DC values. DC meaning they're static values. So we just, they're not real, they're complex, but they are static, so we just add them the way we'd add normal complex numbers. Right, so now let's look at some voltage current relationships for different components. So here I have just a voltage source driving a resistor, and if I plot the voltage and current there, I should see that they are totally in phase. So if I look at the voltage and the current, they should cross zero at the same time. They should peak and trough at the same time. Now, if I look at the phasor representation here, I know the current is equal to the voltage over the phasor impedance. The phasor impedance for the resistor is R angle 0. If you go back a few slides, you'll see where we derive that. So then I have V, and let's say that angle is whatever theta V over R angle 0, and this will give me V over R angle theta V minus 0. So that is V over R angle theta V. So the I is the same value as the phase shift of the I is the same as the phase shift of the V. In other words, they are both in phase. For the inductor, if I do the same thing, so I get I is equal to V on Z, that will be V on omega L angle 90. Now assuming this angle here is 0, then I will see that that is V on omega L angle minus 90, because remember, I'll get V on omega L angle theta V minus 90 since you're dividing, and I'll get V on omega L angle, if this is 0, minus 90, which means the current lags the voltage by 90 degrees. In other words, if I look at the current and the voltage, if the voltage starts here, then after 90 degrees the current will be in the same point. So here the voltage gets to its peak and is coming down. 90 degrees after, the current gets to its peak and is coming down. And for the capacitor, you'll see that the opposite happens. So for the capacitor, I have an angle of minus 90. So when I divide these, I end up with a positive 90, which means that the current leads the voltage by 90 degrees. And this is just simply the opposite phase shift as lag. So here, the current, when it gets to this point, 90 degrees later, the voltage gets to that point. So if we notice the directions of the inductive and capacitive currents, these oppose each other. So if I have the voltage here, the same voltage, and I put a resistor, the current will be in phase. It will be in the same direction. The capacitive current will be 90 degrees ahead, and the inductive current will be 90 degrees behind. Now notice where we put these values. So if I look at rotating this way, so it means I'm taking this entire orientation and rotating it in an anti-clockwise direction. If I choose a point, say here, first I will have the C passing, then the V, then the IL. So the IC passes first, then the VRMS, then the IL. So that's why we say the IC leads, then the VRMS, and then the IL lags. And we'll see the importance of this a little bit later on when we get to things like power factor correction. So one of the things that you will need to know, and one of the things that is very useful for power systems, is phasor diagrams. This is where we could graphically see the voltages and currents. So if I have, say, this simple RL circuit, so I have V, which I can represent as a phasor. This is some V cosine omega t. I could represent that as VRMS angle 0. if I have R and L, then I know the phasor impedance is R plus j omega L, which is ZR plus ZL, which is some Z angle theta Z. And then I could find the current by simply V on Z, which is I angle minus theta Z. So notice here how we did this just like a DC circuit. If it was a DC circuit and I had a DC voltage driving a resistor, I would just say I is equal to V on R. So I didn't have to go through the whole thing with all the sine waves and differentiating to get the L di dt and the C dV dt and all of that. I just said V on R. And here, this is what phasors allow me to do. I is just V on Z. And then I could calculate directly what my current is. So once I get that, I will have some V, which is, say, V angle 0. Let me write it here. This will be V angle 0. And then I worked out my current to I angle minus theta Z, as I have here. Then I could draw these two on a phasor diagram. So I just simply draw V angle 0, and I know I have some negative angle for my current. So I and there's this angle theta Z. So this is the voltage, the source voltage, and the current on a phasor diagram. I could represent the others as well. So I know that R, the voltage across R, VR, is equal to I, the phasor current, multiplied by R, which will give me something in the same direction as R. So VR is equal to IR, which will be I, the magnitude of I by the magnitude of R, with the angle of minus theta Z, which is the same angle as I. So I will get something here, and this will be VR. And then VL, which is I by XL, will be I, magnitude of I by magnitude of XL, by the angle of XL. When I add that in to the angle here, it would be minus theta Z plus 90. So to the angle of minus theta Z here, I add 90 degrees and I will get something going this way. And this will be my VL. And what I should get here, if I plot all of these to scale, is that VR plus VL is equal to the V source. So that is an easy way to tell that everything is correct, because the voltages should all add up. You should actually see Kirchhoff's voltage law here graphically, because you have VR, you have VL, and it should come back to meet this point on your source voltage, because that is what Kirchhoff's voltage law is actually telling you here. And that is one of the things that we'll want to see in all your phasor diagrams. So just to summarize, we had to sketch the steady-state sinusoidal voltages for RL and C components. Derive, you have to know how to derive the phasor form of the impedances. That is just to change to the complex the exponential notation, and look at what would be the value of Z, and to convert between the time domain and phasor domain representations, which is just to pull out the RMS value and the phase from your sinusoidal representation and put it into the phasor form, and then represent voltages and currents on a phasor diagram, which is basically just to look at the phasor, plot the magnitude and phase on a diagram, and then look at the relationships between them. You should see Kirchhoff's voltage law. It is important to note